Hello grade 12s and welcome to our lesson today, and what we're going to be looking at is momentum and vertical projectile motion. So we have a lot to get through, okay? So what we're going to jump right in there, and the first thing we're going to look at is some terminology to do with momentum. So I've got some words here: momentum, law of conservation, elastic collision, inelastic collision, impulse. And what I want you to do is, for the next 3 minutes, I want you to quickly discuss in your groups what you think those terms mean. Okay, so you've got 3 minutes, and then I'll see you after we've discussed it. All right, so grade 12s, we've had a bit of a discussion. So now what we're going to do is let's see how far you got with that and whether you were on track. So now I'm going to remind you of some very important definitions. And the first one is that momentum is defined as the product, okay, so this is important. You've got to have the word product of an object's mass and its velocity. So it's two things that are important. The symbol for momentum is P. All right, and it's lowercase p. Be careful here, not capital P. That means power. And momentum is mass times velocity. What's really important here is that it is a vector, so it has both magnitude and direction. Usually, its direction is the same as the velocity. In fact, there's no exception to that. We've just got to be careful when we have a change in momentum, okay? With the units for momentum, it's a special little unit because momentum doesn't have its own unit like kilograms or joules. It's taken from the units of mass and velocity. So the unit for momentum is kilograms, which is the unit for mass, and meters per second, which is the unit for velocity. Okay, so we're all okay with that. Now, if an object changes its velocity, it will experience a change in momentum. That velocity change doesn't have to just be in magnitude. So I'm not saying to you it needs to be that it's going at 2 meters per second and now it's going at 1. It can change direction and still go at the same velocity in magnitude, in size. So be careful there. It's a vector direction is very important. But how does it change velocity? Well, this is where we get to Newton's second law. In order for the velocity to change, there must be acceleration. And for an object to experience acceleration, it must experience a net force. Okay, so there must be a force on it. And remember that net force from grade 11 is MA. Okay, now A is actually the change in velocity over the change in time. So if I put I put change in velocity instead of A into my equation. So what I'm going to do is just take that A away, and over here I'm going to put change in velocity over change in time. I've developed a new equation, and this gets me to Newton's second law in terms of equilibrium. So there we go. So the page doesn't want to extend for me at the moment. We'll carry on. So I'm going to do it over here. Technology. We love technology. Has its moments. So let's do this. F net equals, I'm just going to write it a bit nicer for you, change in velocity over change in time. Now, m delta v means that the velocity, the momentum is changing. Okay, so over here, this part here, that is change in momentum. So I can write it like this. Okay, now I've written it like that. That gives me my new equation, my next definition, which is Newton's law in terms of momentum. Net force is equal to the rate of change of momentum. Rate of change means divide by time. Okay, rate of change, divide by time. All right, now we're going to talk about the conservation of momentum. This is really important. This is going to come up. And this is how I describe it to my learners. Science is a very special planet. We keep things so they are in the ideal world. We leave out a lot of external things because we don't quite have the maths yet, okay? We don't want to add calculus. We don't want to add a whole bunch of other things to it. Just make it difficult. Conservation momentum happens when two objects collide with each other. So car crashes, you're going to love these questions because it's going to be car crashes and rifles and guns. It's quite a violent section, I have to be honest. But when two objects collide, the two objects have to have had momentum. Maybe it was a zero momentum because the one was stationary, but they have a certain amount of momentum. Because they now exert a force on each other, and that's from Newton's third law, whichever force the one exerts on the other exerts on each other, okay? There's a net force acting on the objects. That net force is going to cause a change in momentum. Between the two objects, though, what's really, really, really important is my total momentum of the system cannot change. We only deal with systems where the external forces are not available. So we ignore external forces. So we're pretty much going to go that if two cars crash, we're going to pretend the drivers didn't see each other and they didn't apply brakes. Not the way you want to learn how to drive, by the way, grade 12s. Okay, so we're going to exclude friction, we're going to exclude external forces because it makes it easier. And what that means for us, though, is that because we're ignoring our external forces, the total linear momentum, next very important word, in an isolated system remains constant. It is conserved. How do we put that into an equation? Now, this is very important. The science that we're doing, now watch what I'm going to write, is I'm going to say sigma initial momentum, okay, or before, is equal to sigma momentum after, okay? What that is a, you know what, this thingy, technology is not my friend again, just saying. No. All right, we're just going to go with this as it is. It really doesn't like me today. So, sigma means total. This is very important. You can also write it as this, which is actually what I do with my learners sometimes as well. Total momentum before equals total momentum after. Okay? With this total, I take each section that I have, I calculate the momentum, and I add it together. Direction is very important. How this equation now changes depends on the situation. So we can develop new equations. There we go. See, if you're just nice to technology, it's nice to you. If we have two separate objects that then collide and move off as separate objects, then we would say that my first object plus its initial velocity plus my second object and its initial velocity is going to be equal to, let's just get rid of that black spot, the first velocity objects and its final velocity plus my second object and its final velocity, okay? If the two objects were separate, come together, collide, stay together, which often happens in car crashes, then I would say that I then can actually add the two masses together because the velocities are the same. So I don't need to worry about it. The science that we're testing is this part. That's actually the equation. How you manipulate the equation depends on the question. Okay, so there's actually lots of ways the second equation, part of the equation can be written, but it all depends on what's happening, whether they stick together, whether they collide. So that is question based. Don't learn the first equation I wrote in green. Don't learn that. Learn total momentum before equals total momentum after. Okay? That brings us to elastic and inelastic collisions. Because we're looking at the terms elastic and inelastic, I'm referring to kinetic energy. Okay? Kinetic energy is very special. Energy is always conserved. Okay? Energy cannot be created or destroyed. It can simply change from one form to another. With elastic, inelastic collisions, all I'm concerned about is kinetic energy. In an elastic collision, kinetic energy is conserved. Okay? In an inelastic collision, conserved, that is spelled right. In an inelastic collision, it's not conserved. What do I mean by that? With an elastic collision, my total kinetic energy initially will be equal to the total kinetic energy afterwards. Okay? With an inelastic, my total initially will not be equal to my total. No, that's not an E, that's terrible. Okay. Oh, no, that's still an eraser. That's a bit silly. No, don't want those. There we go. Can you see we're getting back into the swing of things? It's been a while since I've done this. Okay. Here, we need to now remember what the equation for calculating kinetic energy is. Okay, and remember, kinetic energy is a half mv squared. So with elastic and inelastic collisions, we need to look at how much kinetic energy we had before and how much kinetic energy we had afterwards, and then compare them. please be careful here, guys, because it's so easy. As they say in the question, prove that it was elastic, inelastic, and you start with this section over here. You go EK before equals EK after, and you do your equation, and then your numbers don't match. Mathematically, that's incorrect. And if it's mathematically incorrect, then it's wrong, and they're not going to give you the marks. That is a problem. Okay, so be very, very careful. Once again, also remember that you need to put all the subscripts, M1, V1, MA, VA, whatever we've labeled the systems as. Okay, so that brings us to impulse. Now, impulse is such a strange little thing in momentum, and because impulse is the only thing that you deal with that doesn't have its own symbol. There's no symbol for impulse. Impulse, its symbol, if you want to call it that, is from its definition. Now, its definition is the product of the net force and the contact time. So impulse is product of the net force times contact for time. All right, that's what impulse is. But where do we get impulse? Well, impulse is actually equal to change in momentum. It's a very important concept. Impulse is equal to change in momentum. And if you look at this, and I'm just going to rewrite here, if I go F net equal to M delta V over delta T, Newton's second law in terms of momentum. Okay, same thing. Why is impulse important? Well, before we get there, first I need to remind you, the units of impulse, Newton seconds. It is equal in value to the change in momentum, okay, equal in value, but it has a different unit. It will be the same direction. Why do we need impulse? We use it with airbags. That's why cars have airbags, because when a car crashes, it's going to stop. If I can make the stopping time bigger, then I can make the force smaller, because the change in momentum is going to be the same. Okay, that's really, really important. And I think we've done enough for now. We're going to take a short break, and when we come back, we're going to look at vertical projectile motion. Okay, so I'll see you in a second. Okay, welcome back. Now let's go into vertical projectile motion. So this time I'm not going to give you as much time. We've got two important terms. So I'm going to give you a minute and a half, okay, 90 seconds, and I want you quickly to discuss, okay, 90 seconds, no, let's make it 2 minutes. I'm going to be generous. So 2 minutes, and you are going to now I want you to discuss the terms free fall and projectile. Okay, so you've got 2 minutes, and we'll see how you did in 2 minutes. Let's go. Okay, so now you've discussed those terms. Now we're going to see how well you did, because now I'm going to explain them to you as well, okay? Now the first one was free fall. Any object that is acting under the influence of gravity alone is said to be in free fall. Guys, what that means for you, don't think of free fall as just being an object being dropped. When I throw an object up into the air, if the only thing that's acting on it is gravity, it's known as free fall. Normally, though, we think of it as dropping. It just means that the only force acting on it is gravity. That's really important there, okay? So what that means for us is that brings us to vertical projectile motion. Now, if an object is thrown, projected, that's where the word comes from, shot upwards, downwards, sideways, in the air, okay, it's said to be a projectile. The nice thing about your curriculum is that it's only going to go up and down. They've taken out going at an angle, which makes it so much easier. That makes the math so much easier. What's important though, projectiles are objects under free fall, which means the only thing acting on it is gravity, and that acceleration due to gravity is always, not sure if you're getting this, always 9.8 meters per second squared down. Okay, it cannot be anything else. What's important here is we give you multiple choice questions and we say to you, an object's thrown up in the air, what's the acceleration of the object when it gets to the top of its motion? Because remember, it's going to go up and then it's going to come down. And you go, oh, it's got to be 0 because it stopped. But think about this. If it's 0 when it gets to the top of its motion, how's it going to come back down if the acceleration is 0? It's always 9.8 meters per second squared down. There is no exception to that, okay? Now, whether you're going to use it as a positive acceleration or a negative acceleration depends on which direction you decide to be positive, okay? And that's the important thing here. Everyone does this slightly different. There is no wrong or right to it. You need to get comfortable with this so that you do the same thing every time so you know where you're going, okay? Now, with vertical projectile motion, we're going to use equations of motion that look like the ones we used for equations of motion in grade 10, all right? I've just realized that I need to actually make a change here. The difference here is that it's not delta x, it's delta y. On your information sheet, they'll give you both. They'll give you the equation with delta x and delta y, but these should be delta y. Now, the reason why I'm changing it to a y, in maths, x, your horizontal plane is x, your vertical plane is y. We're looking at vertical. So instead of x, we're going to use y. It just tells me about direction. That's the only difference. The equations work exactly the same. You may see some teachers or educators go, instead of putting a, they put a g. It's not preferred. Okay, the thing here, what you need to remember is that A is always 9.8. It's an implied piece of information in your questions. So you need to be careful there when it comes to working that out, okay? So, I can't even begin to express this, and we're going to do a problem together now. Always choose a direction as positive and stick to it. You can't change your mind halfway through the question and go, well, down was positive for this part, but now I'm going to make up positive. You can't do that, because then when you do your substitutions, the marker at the end of the year is going to mark it wrong because you've now changed your sign convention. So what should be positive has become negative, and that doesn't work, okay? So let's dive into a question straight away. Okay, I'm not going to give you any time to do this one, but I'm going to do it with you, and we're going to see how we go. So Marshall stands on a platform, kicks a soccer ball 6 meters above the ground, position A. So they give you position A, all right, vertically upwards into the air with an initial velocity of 4. So onto our diagram, we say, fine, over here, my initial velocity is 4 meters per second, and it's going up. The ball hits the ground at position D, 1.6 seconds later, the motion of the ball is represented. Straight away, decide on a positive or negative direction. My convention is I go, whatever the initial direction was, that is my positive. So I'm going to choose, and I'm going to write it over here, I'm going to choose up as positive. This is for me. What that means for me is that throughout this question, my acceleration is minus 9,8. That's not going to change. Whether I'm looking at it going from A to B or B to C or C to D doesn't matter, okay? It's going to be minus 9,8. So anything going from A to B is positive, anything going from B to D is negative, okay? So calculate the maximum height the ball reaches above the ground. So over here, when we look at this, we go, all right, maximum height, we're looking for position B. We know we've got the 6 meters, so what we need to now calculate is what is that height. So what do we know? Well, we know initial velocity is 4. When it gets to position B, it stops, so final velocity there is 0. Okay, and I've got acceleration of 9,8. So I've got acceleration, I've got initial velocity, I've got final velocity, and I want delta y. So when I go back to my information sheet, I look at it and I go, can't use any of the equations with t in it. So which equation I'm going to use? I'm going to use delta y is not this equation, because I was about to do this equation. Vi delta t squared plus half a delta t. Now, if I look at this, I'm going to go, not a good choice. I don't have time. I could work it out, but for 5 marks, definitely not what they want. So it's not that equation. The equation I want to use is this one. Vf squared equals Vi squared plus 2a delta y. Okay? Vf squared is nice because it's 0. All right. Vi is 4, and it was going up. Now watch here, I said up was positive, so this is minus 9,8 times delta y. Very important here, okay? That's 0. 4 squared is 16. That's minus 19,6 delta y. I'm going to take the delta y over because I want to solve for delta y, so it becomes positive. I would now divide both sides by 19,6, and I'm going to get 0,82 meters. I get a positive answer. Remember, we're looking at position, but what does this positive answer tell me? It was going up. And that's exactly what I expected. It went 0,8 meters above where it started because up was my positive, all right? Now, I haven't answered the question because it said 6 meters originally. So my maximum height is going to be the 0,82 plus the 6. So it's going to be 6,82 meters above the ground. Don't forget the position, okay? So number 1 done. Let's look at number 2. So we've got the same question, and now it says to us, calculate the time taken to reach the maximum height. Well, we know that my maximum height was 0,82 meters from A to B. They just want to know how long it takes to get up there. I want to try and avoid using delta y because what if I got it wrong? What if we didn't get it right? And plus there's an easier equation because look here. Vf equals Vi plus A delta t. Now watch what I'm going to do here. Vf was 0 to get to part B. Vi is 4. What mustn't I forget? This is minus 9,8 delta t. I know I've made a mistake if time works out to be a negative number. So if I don't put that minus 9,8, I'm going to end up with negative time. So somehow, and I know we work on a very special planet with science, we've managed to have time go backwards while it was thrown up in the air. Never, ever going to happen, okay? So delta t, so it's going to be 9,8 delta t equals 4. All right, so I'm going to have to divide 4 by 9,8. So it's going to give me a tiny time, which is 0,41 seconds. Now you go back to the question, you go, well, does that make sense? Considering it only took 1,6 seconds to get down, for it to use 0,41 to get up, That's okay. If I'd got an answer bigger than 1,6, I'd go, ooh, I've made a mistake because that was the total time. All right? There are lots of other questions we can ask you with this, but we're not going to. Ooh, no, I've missed one. Okay, there's actually a third question which we're not going to do, and we're going to leave that for now because it's got to do with graphs. So, what we're going to do is I need you to think about what we've just done. We're going to take a break. Okay, so we've done a couple of questions, and then when we come back, we're going to do a momentum question, but this time I'm going to let you try it first. Okay, so we're going to take a short break, and then we're going to jump into some momentum. So we'll see you in a little bit. Okay, so we've had our deep breath. Right, so now I've got a momentum question for you, and this is what's going to happen. Okay, there's two parts to it. Questions on the screen so you can see it, and I'm going to give you, we're going to split it up, so I'm going to give you 2 minutes to do the first part of the question, and then I'm going to give you 2 minutes to do 2.2, all right? So here's your first 2 minutes, and I want you to do, let's just read the question first, and then I'll give it to you, so we're all on the same track. So we've got a man of mass 87 kilograms on roller skates, moving horizontally, constant speed, great. Sees a boy of mass 22, so it's a little boy, standing in his path. The man grabs the boy and they continue in a straight line at 24 meters per second. You're going to need to calculate the man's speed just before he grabs the ball and then tell me whether it's an elastic or inelastic collision with a calculation. So I'm going to give you 2 minutes and you're not going to do 2.1, so your time starts now. Okay, hopefully you finish with 2.1 because now you're going to move on to 2.2 and you're going to have another 2 minutes to do 2.2. Okay, so your time starts now. Okay, your time is up, and I know we're making you work really, really quickly, but that's good. The faster you can work through these things, the better it is for you, okay? And yes, you might have made some mistakes, but I'm really just concerned that you're getting the important science concepts, okay? Your exam, you have a little bit more time. So I gave you this question, and now we're going to go through the answer. Now, just reading the question doesn't always help us. So the best thing to do, and you need to understand, guys, I can't draw. So we're not even going to pretend I can draw, but what they told us is that we have a man on roller skates. So I like to draw a little picture of what's going on. So here's my little man. I'm not even going to try to draw roller skates because it's not even going to look like roller skates. And they tell me that he's got a mass of 87 kilograms and he's moving towards a boy. And we have a little boy over here of 22 kilograms who is moving, who's not. He's standing directly in the man's path. So that means the boy's initial velocity is 0. Okay. Then there's a collision. Okay, that's the collision, and what happens is the man gets a bigger head and he picks up the boy. So the man and the boy become one object. Like I said, I can't draw, so it's all right. But the thing here is that they become one object. So I need to add the mass of the man, I'm going to call that mm, and the mass of the boy together because they become one object, and they continue off at 2,4 meters per second. Now, I tend to draw my diagrams with everything moving left to right. I don't know why. I think it might be because I'm right-handed. Might also be because we learn to read from left to right. I don't know. I have learners who would have drawn a diagram similar to this and they would be going off to the left. What that means for us grade 12s is that we can't describe any direction here as being left or right because they didn't tell us that. I can describe it as being towards the man or towards the boy, but that's all. So here's my man, okay, and this is the boy. That's, I don't even know what letter that's supposed to be. That's a B, just go with it. There we go. It's a very special B. All right, so what we know here is this is a collision. Momentum is always conserved. We are asked for the initial velocity of the man. And what we're going to do is, because they go off in the same direction that the man was going in when we started, I'm going to make that direction as positive. So on my diagram, that's a positive. What I've just done, this scribble, is for me. This in no way will get me any marks in an exam. Now I'm going to start with, well, how do I set this out? So now we go fine. I'm starting with the fact that we got a conservation momentum. So total momentum before my initial is equal to my total momentum afterwards. Now we need to set it up so we can do some substitution, okay? Beforehand, and let's not do that, it's not going to work. Beforehand, the mass of the man and his initial velocity plus the mass of the boy plus the boy's initial velocity is equal to their masses added together and their final velocity. They became one object, okay? If you don't recognize they become one object, what you do need to recognize is that they go for the same velocity, so your substitution is important there. So the man was, what, 87 kilograms? We don't know his initial velocity. The boy is 22, but he's not moving. Afterwards, it's 87 plus 22, and it's going at 2,4. We've done the signs. This would be 1, 2, 3, 4 marks, maybe 3, maybe 4 marks, depending on the examiner. Now it's a maths issue. So now we're going to have 87 times the initial velocity of the man. 87 plus 22 is 109. We times it by 2,4. I've done this beforehand. So we get 261,6. Okay. And then we try to extend the page because there we go. And we're going to divide by 87 on both sides. Let's get rid of my little black dots. Not pretty. So my initial velocity of the man is 3,01. But this is a velocity. Velocity is a vector. Vector means that I need to have direction. We can't put it left, right, up, down. So we've now got to consider what they told us in the question. So you go back and you say, well, the question said, man moving horizontally, going towards a boy. So we're going to make quite a big assumption here, which I think is quite right, is that the man was going forward. Okay, he definitely wasn't skating backwards. We could have also put, which might actually technically be a little bit better in terms of making sure everyone understands what we're talking about. I would probably say towards the boy is better. Okay? Because then there can be no confusion as to which way he was going. So we've got an equation, we have a substitution, and then we look at the answer with units, don't forget the units, and a direction. Okay? Hopefully we were all okay with that. The next question is really important. Now they say, is the collision elastic or inelastic? Use a calculation to support your answer. This is one where when I mark these, and I'm including my own learners in this, where I just want to cry because I see such silly mistakes. When we need to prove elastic or inelastic collision, we have to prove that the kinetic energy before is equal to the kinetic energy after. It's a proof, like in maths, when you have to prove an equation. And with the proof in maths, you go left-hand side and you go right-hand side, and then you compare them. We do the same here. So with this question, so this is 2.2. I can't state right away if it's elastic or inelastic. There's a 99% chance it's going to be inelastic, but you never know. All right, maybe they've worked out the numbers correctly, so it is elastic. Very rare. Remember that with collisions, because we hear sound, because there's heat, because there's friction, yeah, we lose kinetic energy along the way. So what we do is this. We go, fine, let's do the sum of the kinetic energy initially. That means I'm going to add together the kinetic energy of the man initially plus the kinetic energy of the boy initially. So that means I go to half. I don't know why I keep wanting to draw brackets today. I'm having a bracket day. Everyone has them. All right, so initial velocity of the man squared. Okay, plus we're going to look at the boy with the boy's initial velocity squared. Now, I would need to use the answer I just found, so that's 87, and we said that the man was going at 3,01. And over here, you don't have to show the substitution because, well, the boy wasn't moving. The boy doesn't have kinetic energy, so that's 0. And when we work this out, we get 394,11 joules. We're all happy with that. Initial velocity, initial kinetic energy, not a problem. And also, if you looked at the mark allocation on this question, this was worth 6 marks, okay? Because it's worth 6 marks, then we need to have more than just a simple equation. Okay, so the second equation is really important. I've said that already. The second part is now the kinetic energy after the collision, all right? That's when the man and the boy are now one object. So now we've got to talk about how we write that equation. So sigma, sum of kinetic energy afterwards. But now let's think about this. The man and the boy are one thing. You're welcome to do 2 equations, but we don't need to because they're one object. So I'm going to write it straight away like this. And then watch what I do. So this is a half. I'm going to add the man's mass and the boy again. And then they were going at 2,4, if you remember correctly, right? So that's 2,4. We plug it into our calculator. They're wonderful things. And I get 313,92. Now we've got to look at what the values tell us. So initially, I had 394. I now have 313. give or take the decimals. The kinetic energy has changed. That means that because, and we write it down, you have to write this step. Because my EK initially, the sum of it, is not equal to the sum of the kinetic energy afterwards, my collision is an inelastic collision. It's an inelastic collision. Don't forget to answer the question, because the question was, is the collision elastic or inelastic? You must answer the question. Here's where the problem lies. If you started at the beginning and went EK before equals EK after, and you do all the substitution, you're going to realize that you get two numbers that aren't equal to each other. Mathematically incorrect. Please be careful. What we could always add into this question is, where did that energy go? And it's always to things like sound, okay, or light, though light here would be a bit silly, because if there's light, that means somehow there's sparks flying, which is not going to happen. Or it can be to heat. A lot of this will be to heat. It's friction. Think about what happens when you rub your hands, okay? So there's friction. When two objects collide, lots and lots of friction with cars, sound, okay? Friction, heat energy, very, very, very important, okay? Now, grade 12s, we've done a lot of work. The last thing you've got to remember with vertical projectile motion, we sort of ran out of time, is you're going to have to include graphs. Interpreting graphs, very important. Gradient, area, all of those sort of things, okay? This is about practice, okay? So hang in there, do as many problems as you can get your hands on, and you will be fine. So we're going to end there for today, and I will see you next time.